Hello, yet again we are facing our familiar differential equation, which is a differential equation of order 1, which is explicit. We will try to solve it, but this time we will try to solve it numerically. So now it will be a problem for numerical analysis. We will not try to get some general overview of behavior of this differential equation or of the system which it defines. Rather, we will focus on one specific instance, on one specific solution, which is typically given by an initial condition. So somebody gives us initial condition, which is a point in the plane given by x0, y0, and we are looking for a solution which passes through this point. And if this differential equation is nice, for instance, if it satisfies assumptions of the Picard theorem, then there should be such a solution, and with a bit of luck it will be global, not just a small local solution, and we can look for it. And if we get lucky, we can actually solve the equation, solve it analytically, and get a formula for this particular solution. However, very often we are not that lucky. We cannot solve the equation analytically, and we saw examples like that before. And then we have to turn to numerical analysis and ask for help. So in fact, the topic of today's lecture is the following. We are given an initial value problem. That's another way to put the fact that we have a differential equation and initial condition. And for this initial value problem, we would like to develop a numerical method for solving it. Now, this brings us to the first good question. What does it mean solving initial value problem numerically? Well, the solution that we are looking for, the solution to the given initial value problem, is a function. We would like to see a formula, but that's not something that numerical analysis can do for us, because numerical analysis only produces number and a finite number of them. So what do we actually expect? What is our question? Well, we have to simplify the situation. So we start by actually restricting our attention to a specific interval. And it makes sense, to make our life easier, to call this final point x0 plus t. And of course it makes sense to start at x0, because when we are given an initial condition, we assume that we sort of didn't really care about what's happening before that in applications. So our attention snaps on at time x0, and we want to know what happens on some interval. And this notation makes it clear what the length of the interval is. It's just t, which is very convenient. Now, this is still too much to ask for, so we have to still simplify our question. Instead of looking at the whole interval, we will look at just some points in it that we are interested in. So we will sample it. Okay, definitely we want to know what's happening at x0, and then there is another point where we want to have the information. So we want to know about this value of the solution. There may be another point over here, let's say x2, and we want this information, and so on. We pick up a bunch of points, and the last of them will be the endpoint. So we are interested in this one as well, and there are some other points here. So we definitely want to look at a partition, points x0, x1, and so on. They are increasing, they go one after another, and the last point is traditionally called xn. And this last point coincides with the endpoint of our interval of interest. And we want to know the solution at these specific points. And then it makes sense to ask numerical analysis for approximations of these values. So instead of looking for actual values of the solution, which we usually cannot get, we will ask for something which is hopefully close. So here is an approximation. Let's call it, okay, the point is x1 here, so it makes sense to call this value y1. So for each point in our partition, we will want an approximation for the value of the solution. And we get them somewhere here. Oh, let's say we can go down, over here, and up again, and down, for instance. So we get a bunch of approximations. Notice I didn't put any dot over here, because the first point we actually know from the initial condition. This we know precisely. So that's an easy start. Okay, what do we expect? Well, we definitely expect that our approximations, yi, are close to the actual values of the solution. So yi should be close to y at time xi. This is our expectation, this is our aim. That's the general setup for the methods that we will be exploring this lecture and the next lecture. And once we have this expectation, we can ask whether we met it or not. So it's a natural question to ask, okay, how will I measure success? In other words, how will I measure the error of the method? And well, it makes sense to ask, if I want these two numbers to be close, then I ask about the difference. So I look at the precise value. Notice that we are talking actually about the absolute error here, because the precise value is compared to the approximate value, and we do it at all points. We ask about the magnitude. So for every point in our interval, we will compare the actual value of the solution and the approximate number, and we can see the distance here nicely. That's actually this difference. And then it makes sense to ask about the largest, about the worst case scenario. So we take maximum, and this will be the number that we are interested in. That's the error. It's the global error, because it's the error when we look at this whole situation globally. And as you can guess, later on we will have some local point of view as well. But for now, global error is our focus. Okay? So this is a framework for all the methods that will come, and this is the framework for essentially all numerical methods for solving initial value problems. So we are expecting to get approximations so that this global error is as small as possible. However, today we will focus on specific situation because we want to make things easy for us today. We will introduce just one method. It's a very simple method, but it's actually surprisingly good. In fact, it's a baseline method for many more advanced situations, many more advanced approaches. And moreover, this essential method, this baseline method, is also a very nice opportunity to introduce all the important features and considerations that are connected with numerical solutions of initial value problems. So we start by simplifying our life. We will take not just any general partition like that, but we will take equidistant partitions. We will take the interval x0 plus t, and split it into segments that are of equal length. And therefore, the important parameter at the start is the number of those segments. Once we have this fixed, we can easily determine the size of one segment, which is t over n, and this will be the step size, a very important parameter for our considerations. And then we are in the following situation. We have some x0, and then using the step size h, we pass to the next guy, x1, and again using the step size h, we pass to the next guy, x2, and we keep going until we reach the endpoint of our interval. So it's actually fairly easy to write down the formula for all those points xi. Xi is obtained by starting at x0 and then making I steps of size h. Very simple formula. Now, for a situation like that, we would like to look at a solution which passes through some point x0, y0 and find approximation. So this is a more specific situation. And to give ourselves some inspiration, we will look at a problem. Consider the following differential equation. Y prime is equal to 1 over 1 plus xy, and initial condition y0 is equal to 0. That's a very nice example, because when we look at this differential equation, especially at the right-hand side, we can see right away that this differential equation is not separable. Because, obviously, I cannot write the right-hand side as a product of x part and y part. It's also not linear. This is also obvious. So the methods which we covered here do not help us at all. Now, if you looked at the bonus lecture, you also encountered homogeneous equations, exact equations, things like that. None of these approaches actually help. It's proved that this equation, although it looks rather nice, cannot be solved analytically. So this initial value problem that we see over here, we cannot solve by obtaining formula for the solution that we want, and we have to try to develop some numerical method. By the way, we could also apply the tools that we had in this lecture on analyzing solutions. And you could see that there is a little trouble in the denominator. We have to be careful. And the denominator also serves as the factor which changes sign. So just out of curiosity, if you try to do this analysis, you will see that there are hyperbolas like that, where the sign of the right-hand side changes, and the solutions are increasing here, decreasing here, decreasing here. You can try to think about it. Now, we are interested in a solution which starts at the origin. So we know that the solution will be increasing, but it's not enough because we need better information. We would like to approximate it. How do we do it? Well, we have to first decide on the intervals. So to make my life easier, I will try something nice. Let's say that my interval of interest will be 0, 3, and I will split it into 3 parts. This will make my life really, really simple. And if I'm splitting interval 0, 3 into 3 parts, then the length of one part is 3 over 3, which is 1 important parameter. So here we go, that's our situation. I start at 0 here, and I want to know what's happening on the interval 0, 3. I split it, okay, equally. So we'll pretend that this is an equidistant partition, okay, more or less. And when I split it like that, it's quite obvious that my partition consists of points 0, 1, 2, 3. Okay, here we go. There is some solution, hopefully. I mean, this differential equation is not all that bad, so we expect some solution to exist here. How do we get its approximation? How do we get those values yi? Well, I actually know the first point. It's this one, the point from the initial condition. So let's start with that one. x0 is equal to 0, y0 is equal to 0. And we are done. Wonderful. How do we get to the next point? Well, what kind of information do we have? We are sitting here at this point, but it may be better to look at the general picture. We are sitting at this point. What do we know? Well, essentially we know the differential equation. And the differential equation provides us with information about the slope, about the rate of change of the solution. So when I'm sitting at the point 0, 0, I actually know that at this moment, the slope of the tangent line to the solution, I'll be talking just about the slope of the solution to make my life easier. Okay, so the slope of the solution can be obtained by simply substituting this point into the right-hand side of my equation. So I take the point 0, 0, put it into the right-hand side, which means I'm putting zeros here, and I get 1. So the solution which passes through this point has slope 1. Okay, let's have a look at it here. I know the slope at this particle point, and I decided to call it k. Well, can I use it somehow? Well, I would say that yes. I'm now interested in what's happening with the solution at time x1. So instead of going along the curve, which I don't know, I can try to go along the tangent line. And I arrive here, and I can call this y1. With a bit of luck, I didn't stray too far away from this solution. That looks like a good idea. So here I'm using the slope 1 to pass to this point, which, because the slope is 1, should I have the y-coordinate equal to 1. But let's ask about a formula, because we want to do some calculations. So, how does it work? Well, first of all, I can definitely figure out the next partition point. I know that x0 is 0, and I want to move to the right horizontally. So x1 is just x0 plus h, which is 0 plus 1, which is 1. Yeah, that fits. That's my next point. How about y1? Well, general picture is better. y1 is sitting here on this straight line. And we know from high school or perhaps even elementary school how to figure it out. There is the initial elevation, y0. And then we proceed with the horizontal displacement h, and the slope is k. So slope is k multiplied by the horizontal displacement. That's the formula for moving along a straight line. How does it work here? Well, y naught is 0, the slope is 1, and the step size is 1. So the answer is 1. And we have our next point. x1 is 1, y1 is 1. If you want, you can say it's the point 1, 1, and here you could say it's the point 0, 0, if you want to see it that way. So this corresponds to our picture really well. The formulas and our common sense gave us the same answer, which is always hopeful. Okay, we are sitting here now. We are sitting here, and what can we do? Well, we can actually play the same game again. Because we are sitting here, we can take the point, substitute it into the right-hand side of our equation, and we learn about the slope. So over here we get some slope, let's say this one. Let's call it k again. And using this slope we can move so that we learn what's happening at time x2. So let's say over here this would be y2. And this is an important moment. What we are developing here is an iterative procedure. So the approximation of our solution that we're looking for, those values yi, they will be constructed iteratively. We go one after another. And we also see how we want to do it. We will be going using tangent lines, using straight segments. So let's try to continue with our calculations. The next point. Okay. Right now we are sitting at the point 1, 1. When we substitute it, we learn about the slope here. And the slope, again, is obtained by substituting points 1 and 1 into the right-hand side of our equation. And this gives me 1 here, this is 1/2. That's the slope. Now let's move on. We know x1, the next point is x2, which is x1 shifted to the right by h. In our case, x1 is 1, h is also 1, and the next point is 2. Does it fit? Yes, it fits with our picture, which is a good news. Okay. How about y2? Well, we were sitting at y1, and we want to move to the right with a slope k and a horizontal displacement h. That's the familiar formula. Now we substitute. y1 is 1, k is 1/2, and step size is 1. So the next value for y is 1 plus 1/2, which is 3/2. Very nice. If you want, you can write that to the point, the next point is 2, 3/2. But actually, from a practical point of view, it may be better to just talk about the coordinates. x2, y2, because we will need them anyway. So we were moving with slope 1/2. So we are moving so that the ratio is 2 to 1. I guess in this direction. And at time 2, we decided on this point to be y2. Okay, 1, 2, and this is 1/2. This more or less fits. Okay, what do we do next? Well, we just recycle what we already did. So we are sitting at the point 2, 3/2. We substitute it into our formula in the differential equation, and we get the new slope. What's the slope? Well, I take 2 multiplied by 3/2. This yields 3 plus 1/4, 1/4. So that's the new slope. We are moving at the direction with the ratio 4 to 1. 4 to 1 could be somehow like that. Now, the next time point, x3, is x2 plus h, which is 2 plus 1, which is 3. Yeah, that fits. We reached the end of our interval. Nice. And y3 is y2 plus slope times displacement. y2 is 3/2. 3/2 plus 1/4 times 1, and this is 7/4. So our next point is 3, 7 over 4. And that's it. We just finished our work because we obtained the last point into our numerical solution. Here we go. And that's it. So what we just did, we just discovered a new numerical method for solving initial value problems. It's an iterative method because you keep repeating the same calculation and you keep moving to the right with your solution. This method provides us with pairs of values or with points, and hopefully these points are really close to our solution. So we start with formal confirmation of what we did. Here we go. This is not a definition, this is an algorithm for the Euler formula. Later on we will see why the word forward is sometimes used, but I am not actually using it. So this is just for the case that you encounter it in some book. Euler formula. How does it work? We are given an initial value problem, which means that we know the differential equation, and we know initial value, which is somewhere there. Yes, initial value, why not? We are given interval of interest of length t, and we are given partition size. Given partition size, we determine the step size, yes, exactly according to our formula, or this formula if you want. And then the first point is given, yeah, that was easy. And then there is an iterative procedure. We are repeatedly generating pairs of points which are based on the previous known location. Now the formula for new x fits with our formula for new x. We are just adding h at each stage. And the formula for y again fits our formula. The only difference is that here in this algorithm I actually didn't use k for the slope, and I wrote directly that we are actually obtaining k by substituting into the right-hand side of our differential equation. Because I wanted to keep it simple, but later on in the next lecture we will see more advanced methods, and there it will be really useful to focus our attention on the fact that this is a slope and there will be more slopes, so it will make sense to call them k. But for now I wanted to keep it simple. This is just a simple formula that we substitute into, we put it into a loop, and at the end we get our numerical solution. Now notice an interesting fact, that once we start going, we can actually keep going. We don't have to restrict ourselves to just one interval. We can keep going and get as much of the solution as we want. And this is actually a very valid viewpoint, and I will return to it. We will get to it later. But for now, we need this setup with a fixed interval, just like you can see it in the algorithm. We start with a fixed interval with a fixed partition, and this is really needed if you want to talk about the quality of your solution, if you want to talk about the global error. Okay? Which brings us to the second good question. How good is this numerical solution? And the answer is, I don't really know. Because I do not know the solution. I don't have a formula for it. And therefore, I cannot now show a picture where I would say, okay, here is the actual solution, here is our approximation, it looks really good. So this is a very important question. How do you judge the quality of your numerical solution if you do not know the actual answer? Now, we already encountered a question like that before, so we know it's very important, but we are not really ready yet to answer it. So we will delay it until the next lecture, essentially, and then we will really look at it hard with some tools that we have at hand. For now, I will cheat a little bit. I will pass to another example, which is extremely simple. It's a baby example, but it has the advantage that I do know the solution, and then we can compare and perhaps see something. So our next example is y prime is equal to 1/2 y. Now, if you checked out the lecture on applications, you have seen that this is a very simple differential equation, probably one of the simplest differential equations around. This is the exponential growth. So we know how the solutions look like, we know everything about it. I also specify initial condition y naught is equal to 1. And we know that this initial value problem has a very nice solution, namely yx is equal to e to x over 2. Very nice. If I didn't use the value 1 here, but a different one, then this constant would appear in front of the exponential. So things work really nicely with this equation. Okay, now I'm going to solve it. And for the purposes of, let's say, visualization, I will be interested in the interval 0, 5. But in fact, this differential equation is so nice that I can do the numerical solution in general, in a general setting. That's one of the advantages of exponential equations, that they are really nice to handle, and that's why they are used as test cases for new methods. If you develop a new method, the best thing to do is to try them on the exponential equation, because then you can learn a lot about it in an easier setting. So we have interval 0t, and I split it into n parts, and therefore I get step size t over n. This is not really new. And now let's construct the point, the first one. Well, it's actually given. So x naught is 0, and y naught is 1. That was easy. Now I will not be writing points one after another, because I don't know how many of them there are. So I will simply write down the procedure for generating them, exactly as it is in the algorithm. I could simply substitute into the formulas and leave it like that, but actually it's better to understand it. So let's talk ourselves through it. I'm sitting at the point xi, yi. How do I generate the new pair? Well, the new xi plus 1 is obtained just by shifting. That was easy. How do I obtain the next yi plus 1? I obtain it by using the original elevation and then moving along a straight line. The slope is k, and this is where it gets interesting. What is the slope? I obtain the slope by taking the current point, xi, yi, and substituting it into my differential equation, into the right-hand side. So the slope is 1/2 yi. And this is multiplied by the step size. So this is the formula for generating points. Now, for which indices do I use the formula? That's a good question, and that's actually one part of the algorithm which I didn't address yet, so it's a good question. Well, I'm sitting at the point x naught, y naught. So this is the natural starting point. So the lowest value for I is 0. And by putting 0 here, I obtain x1, y1. And when I have information about position 1, I put it here, and I obtain information about position 2, position 3, and so on. And I keep going. That's the 3 dots. Now, what is the last guy? The last pair which I need is xn and yn. To obtain xn and yn, I need to put here n minus 1. Is it the same as in my algorithm? The answer is yes. Okay? So this all makes sense nicely. That's essentially an algorithm which I can easily input into a computer, and I just let it run, and it will generate points for me. And then I can try different n, and again, easily in a loop, generate new points, and can compare them, and so on. I have a procedure for that. Let's have a look at it. So, here is my maple. 0.5 is the reproductive constant for my exponential growth, which fits. So let's read the setup, and we can see that we are solving differential equation. Derivative is equal half of y. Yeah, that's our differential equation. And now I will ask for a solution, a numerical solution, using the Euler method, when the partition size is 5, on interval 0, 5, and therefore the step size will be 1, which is actually quite a lot. But we will see what it means. Here we go. So, yeah. The procedure told us that the step size is 1. That's a very useful information. And over here we can see the outcome. The blue curve, that's the solution. That's the exponential, e to x over 2. And the formula, the iterative formula, produced points. There should be 6 of them because partition size is 5. 1, 2, 3, 4, 5, 6. And we can see that they are actually leaning away from the solution. I will talk about it later. Why is it so, and what are the factors there? The important thing now is that the output of an Euler method, of any method that we will cover in this chapter is just a bunch of points. This is not really all that easy to visualize, so people usually connect them by segments. So let me show you how it looks like. So this is a better picture. It sends a better message, but we should keep in mind that those connecting segments are just virtual. We do not have any information about the solution there, these connecting lines. They are just essentially telling us how we traveled, but the only information that we have is those circles. Let's increase the partition size. Let's say that instead of 5, I use 35. That's a nice number. Why not? And we can see that our circles, the points, the approximations that we have over here, these dots, that they got closer to the solution. And we can also see that there's quite a lot of circles, so perhaps this is not the best way to do the visualization. Let's increase the partition size to 135, let's say. And this is getting really a little bit messy. The picture is not really nice. So what people actually do, they just remove the circles. They just show the connecting line. And the picture is now much nicer, but it's actually a misleading picture because it sort of suggests that we have this blue curve, which is the solution, and we are approximating with the red curve, which also looks like a function. It suggests that we know the function. Well, we don't know the function. We just know a bunch of points. We have to keep this in mind. But this bunch of points is actually getting really closer to our solution. What if I increase the partition size to, let's say, 335? Well, we have almost a match of the approximate solution and the true solution. So this shows that, at least for this nice example, the Euler method actually does a good job. If we keep increasing the partition size, in other words, if we keep decreasing the step size, then the approximate solution, those points that we have over here floating around the solution, they're getting closer to it. By the way, just like with integration, the real measure of quality is the step size. So that's the natural viewpoint, and we would like to adopt it. But we cannot start with the step size because we need to make sure that our steps actually fit the interval. For instance, over here, if I decided that I want to travel over this interval using this step size, then it may happen that I make one step, another step, and suddenly I cannot reach the end of the interval because it doesn't fit. Okay? So formally, in definitions, in theorems, we have to talk first about the partition size, but then we get the information that we want, the step size. Okay, here we go. The exponential equation is so nice that it actually allows me to figure out how those points look like and compare them to the solution. So let's try it. I will start by factoring out yi from this iterative formula. So yi plus 1 is in fact 1 plus 1/2 h times yi. That's how the iteration works. Now, let's have a look at a few points. Okay, what's the first point? Well, the first point is y naught. What's the next point? The next point is y1. y1 is 1 plus 1/2 h times y naught, according to this iterative formula. How about y2? y2 is 1 plus 1/2 h times y1, according to my iterative formula. But now for y1, I have a formula here. So I substitute, and I see that this factor is actually there squared. It's there twice in a way. And I multiply it by y naught. What happens if I want to know y3? Well, I have to actually take y2 and still multiply it again by the factor. So now the factor will be cubed. So it's in there about 3 times. So for y3, it's there 3 times. For y2, twice. For 1, it's there once. For y naught, it's not there at all. It all fits. So we are in fact guessing, and this can be proved by induction, very easy, that there is a formula for yi. It's 1 plus 1/2 h to power I times y naught. And this gives us a chance to ask, okay, what happens with these points? We have a nice formula for them. When I start increasing the partition size and send it to infinity, of course, that's what I want. There is a little trouble. Let me show you somewhere where the trouble is. Okay, for instance, here. Here we used partition size 3, and we got these 3 points. What happens if I use partition size 4? I get this point, and I get 4 more points. The last one is located here, somewhere. I don't know where. But the problem is that the other guys are like here, and here, and here. So they are not at the same time. The points which I obtain from one partition are not at the same location as points which I obtain from another partition. So it doesn't make sense to ask about the limit here or limit here. The only place where I can ask reasonably about limits is this last point on my interval. So let's do it. How does yn look like? Yn is 1 plus 1/2, and now let me substitute for the step size. It's t over n to power n times y0. That's the formula for the last point in my partition, which is actually the last point of my interval. That's the point t. So this yn is an approximation of solution at time t, hopefully. I look at this and I say, wait a second, that's a sequence. That's a sequence which has index n, and I can see it also here, and the shape of the sequence is very familiar. In fact, when I was a student of calculus, I had to memorize the outcome of the limit for such sequences. And I learned that this, when n is sent to infinity, converges to y0 times e to t over 2. Now remember, we are trying to approximate solution at time t, and we got that it's exponential to t over 2, which is exactly the right number. Now for us, the initial value is 1, so I put 1 here, and it fits precisely. So what we've shown analytically, so we can trust it really, this is a normal, regular calculation. We have shown that when we are doing this business with Euler method, generating points and so on, and we look at the last one always, at the end of the interval, then the last point for increasing number of partitions actually converges to the actual solution. So that's what the picture shows. But now here we have it confirmed analytically. That's very nice. Now, this example was actually too nice and also a little bit boring. I mean exponential. I mean it's a nice function, but a little bit boring. So just out of curiosity, let's have a look at something slightly more interesting. And I will get inspiration from the exponential growth and look at logistic growth. Again, if you look at this lecture on applications, you know what I'm talking about. So here is logistic growth. That's the logistic differential equation. The carrying capacity or the capacity of the environment is 10, just out of curiosity. And we know that the solution is actually something, a curve, a function which curves twice, which makes it more interesting. And we are going to apply the Euler method. And here is the picture. And again, we should focus on the little circles, but to make our lives easier, I also decided to include those connecting segments to give us a good overview of the behavior. Now, we look at it and we say, well, this is not too bad. The solution is now a little bit more interesting, and the Euler method still manages to follow it reasonably well. And let's try to make the step size smaller. Now, in this case, I'm actually specifying not the partition size, but the step size. And you may say, okay, how is it possible? And the answer is, well, the procedure which I'm using is written in such a way that it's nice to the user. I specify the step size that I'm interested in, and the procedure, it chooses partition size so that the resulting step size is as close as possible to the one that I want. So you can see at the start that I asked for step size 1.3, and instead the step size was 1.33333, which is very close. And then everything works well. Now I am asking for step size 0.3, and again the procedure will find the next best step size, and actually it didn't tell me anything, so it didn't change it. The step size 0.3 was actually okay. Is that true? I'm looking at the range between 0 and 12, and when you look at the range between 0 and 12, that's something that you can you can achieve this with steps of size 0.3. How many of them do you need? 0.3 times 10 is 3 times 4, okay, 40, you need 40 steps. In 40 steps of size 0.3, you get from 0 to 12. This fits nicely. And the solution, the numerical solution, the red curve got closer. Let's still lower the step size to, let's say, 0.1. And we see that the output of the Euler method is getting closer and closer to the actual solution. This is very nice. Now, this logistic growth has another advantage. It also allows us to explain a little bit better how the Euler method works. What's the problem with the Euler method? Now, let's have a look at the basic idea. We are sitting at some point, and we decide to look at the slope of the solution and follow it. The problem is that it only gives us information about the behavior of the solution at the starting point of our step. But while we are going in certain direction, the solution may decide to do something else. And the Euler method learns about it only at the end of the step. So when there is some development in the solution here, we learn about it too late. So it's already built into the Euler method that it lags behind development. It reacts slowly to changes in the solution. And we can see it here very nicely. The solution is curving up quite steeply, but it takes a while for the Euler method to notice. But then it does, and it starts going up steeply. And it goes up steeply, but the solution then decides to slow down. However, the Euler method didn't notice, so it was still going steeply and overshot the target. It got too high, and then it said, oh, wait a second, the solution is actually just going very flatly. I don't have to go up like crazy. I can slow down as well. And the solution slowed down, okay? So that's something which is built into the Euler method. It's good to understand this when you are working with it. We will get to this later. Okay, this brings us to the key question. We saw two examples. One was really trivial. This one was a little bit less trivial, but these are just two examples. So what can we say in general about the quality of numerical solutions produced by the Euler method? We have to go back here to the global error, but now we have to be a little bit more precise about the setup. So we are given initial value problem, which means we are given a differential equation and initial condition. And we are also given interval of interest, x0 plus t. And that's the setup which does not change. However, what does change is the partition size. We look at partition sizes of different partition sizes. And then for each partition size, we produce numerical solution using the Euler method. So we are actually producing a bunch of points, xi, yi, but these points are dependent on n. So I should somehow reflect it in the notation in some way. Let's say that I put a little superscript n in parentheses over here like that. So for each partition size n, I'm getting corresponding points from the Euler method. And for each partition size, I ask about the global error. So the global error is the maximal distance between the actual solution and my approximation. But now I'm doing this for each partition size n. And the natural requirement, and actually it's the baseline requirement, something that you really want, is that this global error goes to 0. That's the key question. Is that true? Because if you have a method which doesn't work like that, then it's essentially worthless. So let's have a look at our first definition. We have a numerical method, not just Euler one. This is now general setup. We have a numerical method for solving initial value problems. It works by producing sequences of points. Then we say that the method is convergent if, whenever we apply it to a specific initial value problem and specific interval, and we do it for many partition sizes, and we look at the global errors of all of them, I hope the formula matches, yes it does, then the global error goes to 0. That's the requirement for so-called convergence. All the methods that we will mention here will be convergent. Euler method is also convergent. I am not going to prove it because it will follow easily from another property, and we will come to it relatively soon. Okay? So let's just take this as, let's say, setup, mental setup for how we want to measure things. But we are not just really interested in whether the error goes to 0. You know from previous chapters on numerical analysis that we really want to know how fast does it go to 0. So we now take for granted that all the methods that we will develop will be convergent, because otherwise I wouldn't show them to you. So every method which you will see here today in the next lecture is convergent. But the key question is, how quickly does it converge? So what I'm really looking for is this. If I look at my error not through the point of view of partition size, but through the point of view of step size, then I want the error to behave like some constant times h to the power p. This is really the question that I want to ask. However, I'm not ready to look at it yet, or look at it directly, because it's rather difficult to take your method, for instance, the Euler method, and develop some formula for the global error. We have to use a different way, which is actually closely related to the inner mechanism of the Euler method, or the methods that we will see. Because all these methods, they have one thing in common, and we can see it here in this example. Let's have a look at this last calculation. I was actually calculating here x3, y3. What information did I need? Well, I needed information about x2 and y2, which is over here. I needed to know the differential equation to determine the slope, and I was substituting this point, x2, y2, into it, and I needed the step size, and that's all. So to get x3 and y3, all that I needed was x2, y2, step size, and the differential equation, which is encoded by the right-hand side f. We can see it over here. And that was it. So it means that the Euler method is actually local. That's the key word here. Notice that if somebody cheated and said, okay, let this point be x12 and y12, then the Euler method would simply calculate x13, y13 in exactly the same way without noticing that anything is wrong. This method, in fact, does not really care about the setup. It does not care what's your partition size. It doesn't care about xi, yi. It doesn't care about anything. Only thing it cares about is a specific location and the step size and your differential equation. And it moves you one step to the right by the step size, and it doesn't care whether it's x3 or x13. So this is a new viewpoint, and it goes like that. You are sitting here. This is your point x, let's say x star, y star. I don't want to see indices anymore. There is a solution going this way. So we are sitting here, x star, and we want to move somewhere. We are sitting here at y star, and we want to move somewhere. So how does it work? Well, you take your x, the horizontal coordinate of your location, and you move it to the right by h, by the step size. That was easy. And you appear somewhere over here, x star plus h. You also need to know the new y coordinate. How do you do it? Well, you have to apply some procedure. We have a procedure here for it. And when we look at the formula and we drop this index, it actually works like that. We take the origin location and we add the slope at the origin location and multiply it by the step size. This is the formula for Euler. But we want to see some general setup now. So we just imagine that there is some formula, or perhaps it not even need to be a formula. It may be some procedure. Let's say 5 calculations that you have to do, and you have to juggle them somehow, put them together. This could be simply some process which produces a number. A new guy over here, hopefully close to our solution. The x-coordinate is easy, and the y-coordinate is the outcome of a procedure which we will just call capital Phi. And What are the inputs for this particular procedure? Well, you are solving a specific differential equation, so you need to know the right-hand side. And it does not change, so we use it as a parameter, as index here. Then there are some things which do change. Well, you have the step size. And actually, when you are constructing one particular solution, then the step size does not change also. So we could perhaps also put the step size as an index. However, later on, after we develop one solution, we want to do another solution and another solution with different step sizes. So this age could also change, and it most likely will change once in a while. What really changes a lot, and you also need it, is the location. So this is the general setup for the methods that we will be looking at in this lecture, in the next lecture. These are so-called one-step methods, because you are making one step at a time. You don't ask what's ahead. You don't ask what was before. You're just sitting here, you have this information, and you want to make one step. Okay? So we are looking at the group of one-step methods. These are local by their nature. And because they are local, it also makes sense to ask about local error. Because you are in fact looking at just one step. You are sitting here, you move here in some way. For the Euler method, use the tangent line, its slope, but there may be other ways, and we will see it in the next lecture, for instance. You end up at some point, and you ask, how far am I from my real solution? And that would be the local error, which is usually denoted D. So this is the setup. Okay? There is some solution passing through this point. And it's a solution which corresponds to the start point. So let me call it y star, with star as a subscript. And we are asking, what's the difference between the new value of our approximation, which is this capital phi, that's the y coordinate of this point, and the actual solution. So we take x star plus h and substitute here, and we get this value. This is the local error, the error that we make when we are doing one step. We are actually getting here to a very important point. And okay, I will need some room to show you this point. Let's get rid of this problem. Let me start with the example that I actually just erased. So this baby example, the first picture that we saw of the numerical solution went like this. We have this exponential over here. Then there was a point, a point, a point, a point, and so on. What was really happening? When I was doing the first iterative step, I checked on the slope over here. That's the slope of the tangent line to the actual solution. I took this slope k and I moved by h. And I got x1, y1. x1, y1. Where do I see the local error? The answer is I see it over here. I made one step, and this is the local error. Let's call it the D1 because it's the local error of the first step. How does the second step work? I take the tangent line and the slope of it, in fact, over here, and I use it to move by h. Again, another step. Where do I see the local error? And that's the key thing. What was I actually trying to do? I took the slope at this point, but this is not exactly the same as the slope at this point, in fact. They may be if we are really lucky, but most likely they are not. It seems that the slope here is different. When I compare the picture, yeah, they do not seem to be the same. So what was I doing at the second step? And the answer is, I was actually trying to follow a solution which passes through here. So if the actual solution is called yx, then in my second step, I was actually following a different solution which I can call, let's say, y star subscript. And this really fits my local picture, because my local picture, the Euler method as a local method, is sitting here and does not know about the actual solution which is going elsewhere. This is totally in a different place. So the local method, one-step method, Euler method, uses information only about this point, and it sees the solution passing through it. And here I can see my local error, D2. And this was repeated over and over. So from here, I went to the point x3 by h, and I was using slope at this position. So in fact, I was trying to follow a solution which I could call y with 2 stars. And again, over here, I can see the local error, D3. Now, normally we do not care very much that I'm in fact trying to follow different solutions. We just get some points and we want them to get close to the original solution. But now that we are talking about the error, this is very important because it makes us focus on what is actually happening, and it will help us to understand the definition of the local error. So let's have a look at it. This is really a key question, a key notion. Okay, here we go. So we have a method, but now we are focusing on one-step methods only. So the method is encoded by some formula or some procedure, capital Phi, with subscript f, because we apply it to a specific differential equation. And this one-step method produces estimates. Well, we have some explanation, which is exactly the one that we had over here. That's the setup for the definition. Then we take a differential equation. We pick a point, x star, y star, and we move to the right using the method. And then we compare the y-coordinate of the new point, this phi f, with the actual solution value, and we take the difference. Now, when you look at the difference, we have y with subscript star, that's the solution which passes through x star, y star, and we evaluate it at point x star plus h, which is at this location. Yeah, it fits. So the local error exactly corresponds to these distances that we can see over here in the picture. We have to be careful, so we have to specify what is the solution y star. It is a solution, and we can see it down here, which solves the initial value problem, and the condition, the initial condition says the solution should pass through the point x star, y star, exactly as we have it over here. That's the solution that we are comparing with, because that's the only solution where comparison makes sense. When we are sitting here at this point, and we are making step and inquiring about local error, we actually have no idea that there is some other solution, the one that we want, floating somewhere else. We only see this solution, the special one for this particular point. Okay? So that's the notion of the local error. And that's something that we can study because we have a formula or we have some procedure for this one step, for this phi f. And because we have it, we can analyze it, and we can see what the local error is. But now the question is, what do we want? What do we want to see? Because in fact, we are not really interested in the local error. It's natural to have it here, but we are interested in the global error. So what is the relationship between local errors that we can see here in the picture and the global error? That's a very important question. Well, here actually two things come into play because we have to start mixing the general setup and the local point of view. Notice that the local point of view, because it's just local, it doesn't care about the setup, does not feature partition size. So for the local error, h is the natural viewpoint because you are making step by h. You don't care about anything else, what was before, what goes afterwards. So there is no n in the definition at all. But now we are back in this general setup, in this specific setup with partition size and points xi, yi, and so on. And we look at the global error, and we can see that we are taking maximum of differences. So it makes sense to look at these differences between our approximation and the actual solution. So now these points are of interest. Okay, the third one is here. And we would like somehow to have information about the actual distances between our approximations and the solution, and local errors. Is there anything that we can see, any connection? And the picture sends a message. For the first point, the distance that we want, and let's call it E, so this will be EI, this distance is actually the same as the local error. How about the second point? Let's have a look at this distance. Let's call it E2. So this distance will be E2. what does the picture suggest? Well, we can see the local error here, that's D2, but we can also take this and try to move it here. So we can see D1 here, D2 here. Or you can think of it this way. This is also E1, and we take E1, we move it here, and we add D2 to it. That's also another way to see it. Does it work? Okay. We can see here the distance E2, that's the one. And we move it here, and we add D3, and what we get looks like E3. So E3 is in fact D1 plus D2 plus D3. When we apply absolute value, we learn that EI is less than or equal summation, local errors, but I don't want to use now the index I over here because I'm using I for the identification of the global error or of the local distance. That's the right word. So I'm going to use J, and J goes from 1 to I. I'm getting this estimate, but to make my life easier, I will add the other local errors as well, and I just simply sum up all of them. So those individual distances between my approximation and the actual solution, they are all bounded from above by the summation of local errors. And therefore, when I take the maximum, I get the same relationship. So the global error for partition size n is bounded by summation j going from 1 to n dj, local errors. And that's the relationship I've been looking for. Let's take it a little bit farther. We know already from numerical differentiation, numerical integration, that we are generally trying to find estimates for the error that feature powers of the step size. So let's be optimistic, and let's assume that we have an estimate for dj in the forms of some constant times h to power q. What would this mean? Well, this would mean that the global error is bounded by, now notice that this estimate, if we have it, is general, so we can apply it, I mean it works for all local errors. So when we put it here, we actually take this estimate and we take it n times. And now we are in a familiar position because the partition size and the step size, they are related. We have a formula here, and we can use it to determine n. We just switch positions in a way. Easy algebra. So this is actually t divided by step size times c times h to power q. And one h cancels, and we get a new constant. We do not really care about t here, it's just a constant, times h to q minus 1. And that's important. This shows that if we get a specific order for the local error, then the global error will have an order which is smaller by 1. Now we saw exactly this behavior with integration, with numerical integration. The underlying reason was different, but the outcome is the same. Local error and global error, they are related. There is a change of 1 power. What does it mean? Well, what we want to see really is the estimate for the global error in the form c times h to power p. And what we just did shows that in order to have this, we have to obtain local error, an estimate for it, in the form c times h to p plus 1. This is how things work. Now, before we go on, I have to admit that I cheated here. I cheated a lot. So this is actually incorrect. But the point that we obtained from this incorrect procedure is correct. Okay? So this relationship between local and global error does work. Why did I show a story that doesn't work? Because it's simple. It sends the right message. Later on, I will try to show you a more precise way, and you will see that it's better not to worry about it too much at this stage. Okay? So let's just take it as a fairy tale, which gives us some insight And this insight is not bad. It's actually a good insight. And it's an inspiration for what will come. So here we go. We are ready now. We are ready to learn how to judge methods for solving initial value problems. Here we go. Consider a one-step method. So that's the setting for this lecture, the next lecture. One-step methods. We are doing things locally. For solving initial value problems. It works, okay, the first paragraph describes how this method works. We already know how it works. Now we say that this method is of order P if whenever we encounter a differential equation which is reasonably nice. So let's skip for a second what it means really. So whenever we encounter a differential equation which is nice, then we get an estimate for the local error which is exactly the form that we want here. So in order to determine the order of a method, we have to look at the local error. We find the power at the step size in the estimate, and then we decrease it by 1, and that's the order of the method, because that's the order of the global error. That's what we really want to see. Okay? Let's have a look at some details. What is the problem here? Well, when we are judging methods, we have to be careful, because if you want to judge methods against all differential equations, then all methods will be bad. I will talk about it in the next lecture. I will show an interesting example. Because some differential equations are really beastly, and no matter what you try, it will not really work well. So, what you need to do is to rule out the really bad cases and focus only on reasonably nice differential equations. For instance, and here is something which is obvious, if you want to determine the global error, then in the first place you need to have the solution. What happens if somebody gives you a differential equation which does not have any solution at all? Well, since the differential equation is given, you can simply follow the procedure formally and you generate points, just like we did over here. And you ask, is it a good approximation for my solution? And then you learn that there is no solution. So you got a bunch of points that are totally meaningless. So the first requirement, baseline requirement, is that your differential equation has a solution that you are looking for. And that's why it's important that we had those theorems on existence and also uniqueness, very useful here. So this brings us back to this lecture on Picard theorem. Picard theorem is probably the most straightforward way to guarantee that your differential equation will have a solution. And that's exactly what's this middle paragraph. When we are testing our method, we are testing it against differential equations where the right-hand side is Lipschitz with respect to y on some rectangle and sufficiently smooth. So this guarantees that when we are checking the solution, the numerical solution against the actual one, then the actual solution actually exists. Now, depending on your method, you may be doing simple calculations, hard calculations. So also there is some requirement on the quality of equation because you are using the right-hand side. For the Euler method, we didn't use much, and you will see it later, so we are not too picky about differential equations. Once we have this Lipschitz condition, we are more or less okay. But for other methods, perhaps you want to restrict your attention still to, let's say, nicer group of differential equations, because you may run into trouble if you try some differential equations which are not all that friendly. So for every method, we will look at different groups of differential equations and measure the quality against this group. That's the idea of the order. It doesn't work like universally against all differential equations. This wouldn't really work in practice. Okay, so that's the definition of the order of the method. And this brings us to our Euler method. We have a nice algorithm for generating points, for generating numerical solutions. So we have a nice formula for capital Phi. We have it over here, actually. And the question is, what is the order of the Euler method? In other words, if I look at the local step, what error am I making there? So let's make some room. Finally, we will get to see some proof, because a mathematical lecture without a proof, it just doesn't feel quite right, okay? So let's do some exploration. We are interested in the local error of the Euler method. So let's go back to the definition and see what we need to do. Well, we need to get ourselves a differential equation y prime is equal to fxy. And then we will be testing it. So perhaps we will look at this definition of order, because that's what they are really interested in. And we see that this differential equation is just not any differential equation. The right-hand side is supposed to be Lipschitz with respect to y on some rectangle. So it means that there is a rectangle, and let's assume that it's a bounded rectangle, I cross j. And on this rectangle, the right-hand side is Lipschitz and also nice, smooth. What does it mean? Well, it could mean many things. For instance, and this is like, again, baseline requirement, we expect the right-hand side to be continuous, definitely. So, if the right-hand side is continuous, then because this rectangle is bounded, and we can take it as closed for our purposes, well, let's skip some details. F must be bounded. There must be some constant which is bounding the absolute value of the right-hand side on this rectangle I cross j. What does it mean? Well, if the right-hand side is bounded, then it means that also the derivative of our solutions is bounded. So every solution which passes through this rectangle, while it passes, has a bounded derivative. Will this be needed? Well, actually, not as such. You will see later in the proof that we will need similar information, but about the second derivative. So let's have a look at our differential equation. Can I get information about the second derivative? The answer is yes, because on the left we have a function depending on x, and we can differentiate. We can also differentiate on the right. We can see x here, and the x is also included as a variable for the solution. So we have to use the chain rule for a function of more variables. And the derivative of this by x is the partial derivative of f by x plus the partial derivative of f by y times derivative of the inside function, which is y prime. Now we will need another assumption, and this other assumption will be that those partial derivatives exist and that they are bounded. So that's what we mean by smoothness for the Euler method. For Euler method, this is what I need for this to make sense. And then, if those partial derivatives are bounded, and if the derivative itself is bounded, it will follow that also the second derivatives are bounded for all solutions while they are passing through this rectangle. So that's the technical assumptions that I need for the calculations to work out for me. So what are the calculations? Well, let's have a look at them. We are supposed to take a location, let me draw a picture here, x star, y star, look at the solution which passes through here, this is y star, and that's what's described in the definition of the local error. Let's go back there. So in the last two lines it says that we should take a solution, follow solution y star, on the last line we can see it, and it's a solution which passes through the point x star, y star. We should also make a step using our method, and we arrive here. This is capital phi f x star y star h. Actually, the y coordinate of this point is this. And we should compare it with this point. That's the local difference. So let's have a look at it. Local difference, let me just call it df, is the actual value of the solution over here. And I'm taking this at a time x star plus h, because that's over here. X star plus h. Didn't we have this picture? Oh yeah, over there. Never mind. It never hurts to think about things twice. And I should subtract the approximate value, which is this baby. Okay, here we go. Capital phi f x star y star h. So that's by definition the local error. I sort of deduced it from the picture, and now I check that I didn't do anything wrong. Yes, that's exactly like in the definition. Okay. How much is it? Good question. I don't know anything about the solution y star. What can I do? Well, favorite trick from numerical analysis, Taylor expansion. I'm interested in what's happening when h is really small, close to 0, so that's how I will do my Taylor expansion. Y star, x star, that's the value. Now the linear part, y derivative star, x star times step size h. let's say we take also the second, the quadratic term, the second derivative of y star, x star, h squared, and that should be enough, plus o h cubed. There is some tail that I'm ignoring. So that's the value of the solution. And because I included o h cubed, it's actually a precise description, so I can write equality. Now I'm subtracting the approximation produced by the Euler formula. And for the Euler formula, we figured it out before, that's the formula. So I'm subtracting y star plus f x star y star times h. Okay, what does it mean? Well, what is y star x star? Well, from the initial condition, this is exactly y star. So this number is y star plus. What's the derivative at time x star? Do I see it anywhere? The answer is yes, I see it in my differential equation. So the derivative is in fact f x star y star x star multiplied by step size h. I can see it over here. Plus, how about this guy, second derivative? Well, I actually have a formula for it, but it's too complicated. Let's just leave it like that. 1/2 y double star, not double star, double prime star, x star, h squared plus o h cubed. And I'm subtracting y star, and I'm subtracting f x star y star times h. Now, this cancels, obviously, and this also cancels because y star x star is equal to y star. We already saw it here. Here we can see it the second time. Equality here. So the first two terms, they cancel, and we can see that the local error is determined by this expression plus some error term, which is negligible when h is really small. So roughly speaking, the local error is bounded by, and here it comes, the second derivative of all solutions that pass through this rectangle is bounded by some constant. OH cubed term, this can be incorporated with a little bit of care. If I increase this constant a little bit, then it will also incorporate this OH cube term. Okay? I don't want to go into too many details. This is the main message that we want to see. Or if you want, the f is OH squared, which is OH to 1 plus 1. We just found out and proved mathematically, with little gaps in the proof, that for the Euler method, which is this formula, for the Euler formula, the local error in approximation in one step is OH 1 plus 1. Then when we pass to the global error, which is over here, then according to this fairy tale, the global error will be of order 1. So Euler method is linear. Do I have room for this interesting observation? The answer is yes. Let's put it here. The global error is OH. In other words, the global error can be approximated by constant times h. Notice that this constant that we have here depends on the setup. It depends on the differential equation. It depends on the rectangle where I'm solving. So it's not like that there is one universal constant which works for all differential equations, all solutions. One has to be careful. Okay? The trick is that when they are solving a particular differential equation on a specific interval, then this constant is really a constant. It's just one number, and you can use it to do all kinds of estimates. Okay? So that's the happy end. We just proved that the Euler method is of order 1. Very important statement because it tells us something about this method. Here we go. And in the specification of the theorem, we also have to specify how we measure this order, because as I said, for different methods, we measure it against different groups of differential equations. So how does it work for the Euler method? it says the Euler method is of order 1, okay, with respect to differential equations where the right-hand side is differentiable and the derivatives are bounded. Yeah, that's exactly the assumptions that I needed here to get the boundedness for this term in my error estimate. Okay, so I really need this for the Euler method estimate to work. This boundedness of the derivative of the right-hand side. So it all fits. You can see how it goes together. Okay, that was the end of the proof, in fact, of this theorem. So we can put a little square. We feel much better. Yeah, this lecture is shaping up really nicely. Okay, before we move on, we just proved that for the Euler method, the global error can be, for a specific differential equation, approximated by c times h. What does it mean? Well, it means that if h goes to 0, then the global error goes to 0 as well. In other words, once we determine that a method, numerical method for solving initial value problems, has a specific order which is positive, and we don't care about other orders, okay? Order is always positive here. So once we determine that the global error has a specific order, then automatically this method will be convergent, which brings us back to the, let's say, initial part of this lecture. So now we actually know, thanks to this proof, that the Euler method is convergent, and it works like that for all the methods that we will meet later on. Once we determine the order, we have convergence for free. Okay, that was the happy end. Or perhaps not. This proof is reasonably okay. There are just some little gaps, they can be filled. But then when I was passing from local error h square to global error h, I was actually using this part of the blackboard, which is not really mathematics. This is just a fairy tale. So if you feel bad here about cheating, and I do feel a little bit bad about cheating, in fact, perhaps we should spare a few minutes on this problem of relating local error and the global error. Let's make some room for it. Let's have a look at this picture again. How did I derive the formula that E2, the distance between the second approximation and the second point on the solution, is D1 plus D2? I took this distance, which is E1 or D1, and I moved it here. However, let's have a look at the picture again. We start here, we have our solution, and we move somewhere here. And what we do here is to make an error which is local, but also global. It's the actual error between the approximation and the solution. Then, when we are making the second step of our iteration, we are actually following a different solution. And over here, we commit another local error, D2. But for this trick to work, these two solutions would have to be parallel. But do they need to be parallel? The answer is no. This is the actual solution that we are trying to follow. This is the first local solution. And they can easily spread out, or perhaps they can converge. We do not know. That's the problem. So when we took this, let's say E1, and we moved it here, we were in fact talking about this distance. And there's still a gap that we didn't fill. So E2, which is distance between these points, actual solution, my approximation, E2 is E1 plus D2 plus something. There is another distance which is essentially telling me how far the solutions that start at different places are spreading out or perhaps closing in. And if I want to see some proper mathematics, I would have to ask how large this is and work it out. And it's possible. It's actually a little bit easier to approach this in a different way. So let me show you an alternative take on this situation. I'm sitting here, and I follow my solution. That's the true solution, yx. And I get here. And I see here the local error, D1. Then I move on using my method. So the y-coordinate of this point, and this is important, is phi f, and I used this point, so this is x1, y1, h. Where do I see the second local error? Originally, I saw it here because I was following a different solution, which was natural. But for the calculations, it's actually easier if I now start from here and I do the second step from here. And what is this? This is actually phi f. The starting x coordinate is the same, but for the y coordinate, I'm actually sitting on the actual solution. Y, x1, h. This has the advantage that I don't have to worry about this y star solution. I can still talk about the original solution, the one that I want. And here I have a local error d2, and this error d2 is local, which means it also depends on the starting point, so this d2 may be different from this one. I don't know, but I still have it under control because I have a general estimate. For instance, here I have an estimate that d2 is OH squared, and that's what really matters. So the distance E2 that I can see over here now consists of two components. I can see the error over here, d2, and over here I have the difference between the, let's say, outputs from the Euler method when I have common x but different starting y's. So this distance is phi f x y x1 h minus phi, and here I'm using y1 h. And now here is where it gets interesting. This cannot be handled in general because phi f is some general procedure for one-step formulas. So I would have trouble doing this relationship in general. And therefore, this relationship between local and global error is always determined for a specific method. I need to know how the method works so that I can work out this part in my error estimate. For the Euler method, we do know how it works, and therefore this can be figured out. In fact, if you have some assumptions, you can also figure it out for groups of methods where you have reasonable assumptions. And one good reasonable assumption is that this formula behaves as a Lipschitz function with respect to y. And therefore, this difference will be proportional to the difference between the y coordinate, because you can notice that the x coordinate is the same and step h is also the same. We are only changing the y coordinate depending on where we start. So this is really proportional to the difference between y x1 and y1, and this is exactly the local error that we have over here. So d1 actually makes an appearance, but it will be multiplied by a specific constant. So E2, let me put it here, E2 will be in fact something like d1 times c plus d2. And in the same way, we can handle the third step and the fourth step and so on. So eventually, there will be a summation of local errors, like we had it here, but there will be also some constants. And one would have to keep those constants in check. You would have to find some upper bound for them. So what it really means is that this relationship is more or less true for reasonable methods, for methods where we can handle differences like that. But the constant c does not carry over. It's a different constant now. But we do not really worry about that. We only care about the power at the step size. So this was just to support this fairy tale with a little bit more mathematics. This is not a proof, definitely. There are big gaps, but at least this is closer to the truth. I'm not cheating anymore here. This is a good picture. That's how it really goes, or this picture. Okay, that's it for the Euler method.